Hello everyone and welcome to the 14th logic lecture of Comp 0003. In today's lecture we're going to continue looking at modal logic, which, as you'll remember, is an extension of propositional logic that allows us to talk about possibility and necessity. Now that's usually thought of semantically in terms of possible worlds, and this gives us the idea of a frame of modal logic. And you'll recall that a frame is very like a graph in computer science. Could be infinite, but still a graph. And the vertices of the graph can be thought of as the set of possible worlds or states or situations. And the edges of the graph capture the concept of what is called accessibility between worlds. So the edges show which worlds are accessible from which others. Now, in modal logic, we think of formulas as not just being simply true or false, but we think of them as being true or false at a particular world or in a particular possible situation. So that means that a valuation of the propositions in modal logic can really be thought of as somehow labeling the vertices of the graph. So for every vertex, we label it with the propositions that happen to be true in that particular world. So today I think we'll proceed in the following way. First of all, I'm going to briefly recap the syntax and semantics of modal logic that we saw in the last lecture. And then we're going to pick up pretty much from where we left off last time. I'm going to show some examples of formulas that are generally valid, which is to say valid in all frames, and some that are not generally valid. And then after that, I think we're going to go on to begin at least talking about how it is that various kind of conditions on frames can be captured by formulas of modal logic and vice versa. So I think we'll probably come back to me in a little while, but for now, as always, let's go to the slides. Okay, so let's begin by firstly recapping very quickly the syntax and semantics of modal logic that we saw in the last lecture. Now, the syntax is easy enough because essentially it is just the syntax of propositional logic, but with the two modalities, diamond and box, kind of added into the mix. So that is to say, a formula of modal logic A is either a proposition letter, and those are the atomic formulas, or they're obtained from modal logic formulas by applying negation, conjunction, disjunction, implication, by implication, or by applying one of the two modalities, diamond and box. So if A is a modal logic formula, then so is diamond A, and so is box A. So that's the syntax, extremely simple. Now, in order to give the semantics of modal logic, we first need the idea of a frame. Now, I'm usually writing the notation M to represent a frame, and a frame, as I said at the beginning, is essentially just a graph. So it is a set W of so-called worlds, which must be a non-empty set, and then a binary relation, usually written as R, on the worlds. So it's a set of pairs of worlds. And that's usually known as the accessibility relation of the frame. It tells you which worlds are accessible from which others. And then we have the idea of evaluation. So if we've picked a particular frame, or a particular graph, if you like, then evaluation is a map from proposition letters to the power set of W, which is to say, for every proposition letter, say P, row of P, is a subset of W. So in other words, evaluation for every proposition letter returns a set of worlds, and it's supposed to be the set of worlds where that proposition is true. Now, you'll recall that in modal logic, formulas are not just true or false, but they're true or false at particular worlds in the model. So having picked a frame M and evaluation rho, this notation here, M, W, and rho satisfy A, that means that the formula A is true at world W, and that's relative to the choice of frame and evaluation, obviously. And this is defined inductively on the structure of modal logic formulas. And perhaps the most important clause is the one for propositions. So proposition P is true at world W if, well, remember that the valuation tells us the set of worlds where the proposition is true. So we take row of P, that's a set of worlds, we check that W belongs to that set. So P is true at world W just in case W belongs to the valuation of the proposition letter P. Then we have the clauses for the propositional connectives, and I haven't bothered to write them all down because they are the same as for propositional logic. So for example, not A is true at world W if and only if A is not true at world W. And a conjunction A and B is true at W just in case A and B are both true at W, and so on. You can fill in the rest. And then we have the clauses for the two modalities. So diamond A is supposed to say possibly A, and that basically says there is some world accessible from the current one where A is true. So you can even think of, A holds in one step, perhaps. So formally, the clause is diamond A is true at W if there is some W prime such that W prime is accessible from W, which is to say R, W, W prime, and the formula A is true at W prime. And the case of a box is kind of dual in the sense, sorry, just having a wee drink of water there. Box A is necessarily A, or it kind of means A is true everywhere accessible from the current world. So again, formally, it's written using this quantifier, says for all W prime, such that W prime is accessible from W, then A is true at W prime. So for all W prime, if R W W prime, which is to say W prime is accessible from W, then A is true at W prime. And that's the entire satisfaction relation for modal logic. And you remember as well that we also have concepts of validity and satisfiability, which are quite similar really to the concepts we've used in propositional logic and in first order logic. So we have the idea of being valid in a frame. So for a formula to be valid in a frame means that it is valid at all points in the frame, in all possible worlds, so it's true at all W, and it has to be true under all possible valuations of the propositional variables. So M models A is valid in M if this guy, M, W, and rho make A true for all possible valuations and worlds. And a formula said just to be valid if it's also valid no matter how you choose the frame. So it's valid if it's valid in all frames. There is also a similar notion of satisfiable in a frame and just being satisfiable. We gave those in the last lecture, but I don't think I need to give them again here now. Let's also go on and or just repeat the example that we did last time to finish off, because I think it's good just to get us back into the swing of things. So here's an example of a formula which is valid, which should say valid in all frames, so it's kind of always true everywhere. Box A and box A implies B implies box B. So, I mean, you can see that this kind of makes sense intuitively because if A is true everywhere accessible in one step from the current world, whatever that world is, and A implies B is also true at all accessible states, then B must be true at all accessible states. And that's exactly how the proof goes. So to show that something is valid means showing that it's valid in all frames. So we have to pick an arbitrary frame, we can't assume anything about it. And to show that it's valid in that particular frame means showing that it's true for any valuation and for any world in that frame. So we're going to pick an arbitrary valuation for the frame and let little w be an arbitrary world in that frame. Now what we have to show, just breaking down the propositional connectors, we have to show that if something and something else, then a third thing. So if M, W and rho make the first conjunct box A true, and they make the second conjunct box A implies B true, which I've labeled as facts 1 and 2, then M and W satisfy box B. Sorry, this here I've written as B. I actually meant box B. So showing correctly here that box B is true at world W. Now remember that box means for all worlds accessible from the current one, B is true there. So that means showing that if some arbitrary world W prime is accessible from W, then B must be true at W prime. So that's just what it means to show box B. So let's assume that some world is accessible, call it W prime, we'll show that B must be true. Now, since W prime is accessible from W, and since the fact that W satisfies box A means that A is true at all accessible worlds from W, then W prime must satisfy A. And by the same token, using this fact, the fact that box A implies B is true at W, means that A implies B is true at all accessible worlds from W, and so it must be true at W prime as well. So now we have a world, W prime, where A is true, and A implies B is true. And so it must be the case that B is true at that world as well. And that's exactly what we had to show, and so we're done. Okay, let's do another example of a valid formula, but this time I want to show an equivalence. So, not box A, if and only if diamond not A is a valid formula. So that's the kind of the same thing as saying not necessarily A is the same thing as saying possibly not A. And intuitively that makes sense. If you say that it's not the case that A is true at all worlds, at all accessible worlds from the current one, then it must be the case that some accessible world does not satisfy A. And certainly, if it's possible to get to a world in one step where A is not true, then it certainly can't be true either that A is true at all worlds accessible from the current one. And indeed, the argument is going to be very like this. So again, to show that something is valid means that it has to be valid in all frames. So I'll let M be an arbitrary frame. And showing that it's valid in this arbitrary frame means it has to be true at all worlds in the frame and under all valuations of the propositional variables. So I'll take an arbitrary valuation rho and an arbitrary world W. And what I have to show for this equivalence, just breaking up the if and only if, we need to show that the formula not box A is true at world W, if and only if the formula diamond not A is true at W. And in fact, we're going to be able to do this more or less just by working with the satisfaction relation directly in this case. So I'm going to start at the left-hand side, and I'm going to work my way over to the right-hand side using equivalences. So here's the left-hand side. W satisfies not box A. Well, just by applying the clause for negation, that is the case if and only if the formula box A is not true at W. And that means that just by using the clause for box, we have to say it's not the case that for all accessible worlds W prime that A is true at W prime. So it's not the case that for all W prime RW prime implies W prime satisfies A. Again, that's just that. I mean, there's no work being done there. It's just it's really just applying the definition. Now, if I now here's the part where we do like a little piece of reasoning, which is also similar to the reasoning that we've done in first order logic. Is if something is if it's not the case that A is true at all accessible worlds, well, that exactly means that there is some accessible world where it's not true. So that must mean if this is not true, then this is the case if and only if there is an accessible world So there is a W prime which is accessible, and A is not true there. To say that something is, say that A is not true at all accessible worlds is exactly the same thing as to say there is some accessible world where A is not true. So there exists a W prime such that R W prime, but W prime does not satisfy A. And you can check that this works in both directions. This is the kind of the main, this is really the main important step here. And just by, I mean, obviously, but I've tried to put here because I kind of thought it's significant to point out the fact that W prime does not satisfy A. But of course, but logically is exactly the same thing as and. So there's an accessible W prime that by the clause for negation satisfies the formula not A, because not satisfying A and satisfying not A are exactly the same thing. And that, by applying the clause for diamond, there is a world which is accessible, and where not A is true is exactly to say that W itself satisfies diamond not A. So we've gone from the left-hand side to the right-hand side, only using equivalences. I could also have kind of worked my way from the right side to the left-hand side doing this. And so that's what we needed to show. And so we're done, and this formula is valid. So this also lets you put push negations inside modalities, or the other way around. So you can push a negation inside a box. By the way, I won't bother to show it, but as a little exercise, you might want to show that this actually works as well if you swap the box and the diamond in this lemma. So not diamond A is the same thing as box not A. So if it's not the case that A is possible, then necessarily A is false at all accessible worlds, and vice versa. Now let's do an example of something which is not valid. How might you show that something is not valid? Well, you have to show that it's not valid. There's at least some frame where it's not valid. So here's an example of something that's not valid. Box A implies diamond A. If something is necessary, then it is possible. That sort of seems like it might be true, and in some frames it is true, but generally it's not, and let's see why. So to say that it's not valid, I mean, here I can take any formula A, because if I can find at least one formula A where it doesn't work, then obviously it doesn't work for all A. I need to find a frame where it doesn't hold. So that means I'm allowed to choose a frame such that this formula is not valid in that frame. And to say that it's not valid in the frame means that it's not valid for all valuations. It's not satisfied by all valuations and at all worlds. So, and of course, because it's an implication, it means I need to find a frame and a valuation and a world in the frame, say W, such that W satisfies the left-hand side of the implication, box A, but it does not satisfy the right-hand side of the implication, diamond A. So, as my frame, I'm going to take an extremely simple example. I'm going to take a frame with exactly one world, which is going to be, say, W. I'm allowed to choose it because, I mean, this is definitely a frame. If it's not valid in this frame, then it's certainly not valid in all frames, and therefore it's not valid. And as my accessibility relation, I'm going to take the empty set, or the empty relation. So there's only one world, but so this just means that W is not accessible from itself in this case. So it's really, so it's just the frame consisting of one world by itself, and that's all. So we can actually see that the formula box A is true at W. It doesn't even matter what A is, so we don't have to be fussy about what formula A we pick. Anything will do. Box A must actually be true because box A says that A is true at all worlds accessible from W, and that is trivially true for the reason that no worlds are accessible from W. I mean, again, it's like the case of empty quantification, where I can say correctly all the unicorns in my office are blue. And that is true. It's a true statement for the trivial reason that there aren't any unicorns in my office. If you wanted to argue that what I said was not true, I said, well, no, James, not all the unicorns in the office are blue. Well, I would say then, well, then you have to show me one that is in my office but not blue. And of course, you wouldn't be able to do that. So box A is true because trivially, A is true at all the worlds accessible from W, which is to say no worlds at all. However, for the same reason, the formula diamond A is false, because diamond A says that there is some world accessible from W where A is true. And that can't possibly be right because, again, there are no worlds accessible from W. So we definitely can't find one where A is true. So we've managed to construct a frame and a point or a world in the frame where the left-hand side of the implication is true, but the right-hand side is false. So the implication itself is false at that point. That means that it can't be valid in that frame because it's not valid at all points in the frame, and therefore it's not valid either. So in order to show that something is not valid, a single counterexample is enough. And sometimes you might have to do a bit of work in inventing that counterexample, but you do at least have the freedom to choose. Okay, so here's another slightly curious example. The formula box A implies A is not valid. Let's see why not. In fact, almost the same counterexample that we used in the previous example is still going to work. We just have to modify it a little bit. We're going to take the same frame as last time. So we're going to take the frame, again, we have to show that it is not valid, meaning that there's at least one frame where it's not valid. And that means we have to show that it's not valid in that frame. We can find some example of a formula A that where the axiom or the formula is not true, and we're allowed to choose a valuation, and we're allowed to choose a point. And it's enough to show that the formula fails to be true at just that one point under one valuation, then it can't be true in the frame. So we're going to take the same frame as before. So the frame consisting of one single world, W, and the empty accessibility relation, so W is not accessible from itself. For my formula A, I'm going to kind of need this. I'm going to choose A to be a proposition, P. And generally, by the way, this is quite a good strategy, because generally, if you find that if in modal logic some formula is not valid, then it's also not valid in the case where the formulas or the formula letters or variables are just propositions. Now, the reason that I've chosen this frame the same way as I did before is because I want the formula box A to be true, and I know that the box A is going to be true in this at W in this frame for the reason that that no worlds are accessible from W. And I'm going to choose a proposition P because I know that I have to try and somehow make the right-hand side false. So if I take A to be the proposition P, and I take the valuation of the proposition to be empty, so proposition P is true at no worlds in the frame, then I know that I know that P is going to be false everywhere. So W still satisfies box P because P is true at all the worlds accessible from W, because there are no worlds accessible from W. So just for a kind of empty reason, W satisfies box P. But now, obviously, W does not satisfy P because W is not in the valuation of P, because we've chosen the valuation to be the empty set. In fact, we've chosen it deliberately to make sure that the W does not turn up in the valuation of P. So that means that the implication box P implies P is not true at world W, and so it's definitely not true for all formulas A. So it's not valid in this frame, and therefore it's not valid because it's not valid in all frames. On the other hand, I mean, you can kind of say, well, okay, it's not valid, but it does sort of seem like maybe it should be under any kind of under a lot of kind of philosophical readings of the formula. You kind of say box A says that A is somehow necessary. So one way of reading saying of box A implies A, saying that if A is necessary, then it is also true. And somehow that does not seem completely unreasonable kind of thing to want to have in your logic. But I mean, as a matter of fact, you know, the way we've defined things is not true. But you might think, well, maybe it should be true. Another way of looking at this formula, you can kind of turn it round. If you turn the implication around and play around with negations and things like this, a good exercise will be to for you to show that this formula is equivalent to A implies diamond A, which says that if A is true, then it is also possible. Again, that seems kind of reasonable, but for the same reason as above, it's in fact not valid. So it's worth thinking about whether we can kind of tweak our logic so that it is. Hello again. So I wanted to talk a little bit more about the previous example that we saw, and that was the failure of the implication box A implies A in modal logic. So it's not the case that if A is necessary, then A is true. So if A is true at all accessible states, it doesn't mean that it's true now. And we saw some we saw one counterexample of why not. But actually, you can think that this principle might fail in modal logic because of two main kinds of countermodel. Now, the first is the countermodel that we actually used, the example where you kind of have a state W, where nothing else is accessible from W, and where A does not hold. So in that case, box A is true for the empty reason that all states accessible from W have the property A, simply because there are no accessible states, and A itself is not true at the world W. And the second kind of counterexample is this guy here, where again you have a state W where A is not true, and then you do actually have some number of states or worlds that are accessible from W, and A happens to hold all of those. Now, how might you get around this? Let me grab a pen. Okay, well, I mean, you might look at this first example and kind of say, well, box A is true at W here, but it's true for a kind of bullshit reason. It's true for the kind of stupid reason that there aren't any states accessible from W, and so it's an empty quantification. And you might kind of furthermore say, and what's more, James, I'm sick of your fucking ridiculous statements about unicorns in your office and all the rest of it. So I'm going to make sure that from now on, when you say all states, you're going to be capturing. You're not talking about an empty set of things. You're talking about at least one thing. And the only way that you can really fix that here is to make sure that W is accessible from itself, because there's no other choice. So if we add a kind of self loop like that, so we say that W should be accessible from itself at least, well, then of course A is still not true at world W. It didn't change that, and we can't change that, but it doesn't matter because box A is now no longer true at W, because W is accessible from itself, but A does not hold there. So that's one kind of, so we could try and get out of that counterexample in that way, but actually you kind of, that still leaves the difficulty of the second example. So you're saying, well, all the states accessible from W, which is not an empty set, they all satisfy A, but W itself does not. And so, I mean, how to fix this? Well, actually, you could fix it in a similar way. If you insist that W is accessible from itself by adding a self loop like this, well, now you're kind of saying that that all the states reachable from W have got to include W as well. And so now, again, A is still false at W, but so is box A, because W is accessible from W, and A does not hold there, so that's okay. It's worth noting that then if you're going to take that approach, then you'd also have to add these same self loops to all the other states, like this. Otherwise, I would be able to play exactly the same game. And in fact, we'll see quite shortly that that if you add these self loops, and that makes the frame what we call reflexive, then that completely gets rid of all the instances where box A does not imply A. In fact, you can go further than this, and you can actually show that this formula, box A implies A, is valid in a frame if and only if every state in the frame has got one of these self loops. So let's go and have a look at that now. Okay, so the way we've defined modal logic up to now, I said before that there are quite a lot of different modal logics in the literature, and here we've basically chosen to look at the simplest one, and it's also kind of the weakest one in the sense that it kind of makes the least set of formulas kind of valid. And for historical reasons, which I now have no idea what they are, modal logic, as we've defined it here, is most commonly called K, the modal logic K. However, as we've already seen, it might be that that some formulas in K are not valid, even though for practical reasons or philosophical reasons, we might kind of want them to be valid. And as I sketched in the previous segment on the board, if we impose some extra conditions on our frames, we'd rather than just saying, you know, they are graphs, but if we instead say they are graphs with some specific mathematical properties, then that has the effect very often of strengthening the modal logic in the sense that formulas that were not previously valid become valid on this restricted class of frames. Now, this actually works the other way around as well. You can kind of say, if I take one of these formulas as an axiom, then that kind of causes all the frames to be restricted in a certain sense. So we're just going to see one particular example of this today, which is the example which we sketched on the board before. So we say that the accessibility relation, or any binary relation actually, is reflexive if for all worlds W, W is accessible from itself. So R always contains an edge from every world in the frame to itself. And a frame is said to be reflexive if the accessibility relation R inside the frame is reflexive. So something which is really easy to establish is that the formula box A implies A is valid in every reflexive frame. As we already saw that it's not valid in every frame, but it is valid in every frame that happens to be reflexive. So to show that it's valid in every reflexive frame, we will take an arbitrary frame and we're allowed to assume that that frame is reflexive. So we'll let W and R be a reflexive frame, meaning that that R is a reflexive relation. And we have to show that the formula box A implies A is valid in that frame. That means showing that it is valid, that it is satisfied by all points in the frame or all worlds in the frame and under every possible valuation. So let's take rho to be some arbitrary valuation, and let's take little w to be an arbitrary world in the model. And because we're showing an implication, box A implies A, that means showing that if box A is true at the world W, then so is A. Now, I mean, actually, here's the proof in sort of another 2 lines. So let's assume then that the formula box A is true at W. So we have to show that A itself is true at W. Now, since the frame is reflexive, meaning that the relation R is reflexive, W is then accessible from itself. We have R W, W. And since box A is true at W, meaning that A is true at all worlds accessible from W, and since W is accessible from itself, that means that W itself must satisfy A. And that's exactly what we wanted to show. So there's a very simple proof here that the formula box A implies A is valid in every reflexive frame. And as an exercise, you may like trying to show, with a slightly different proof, I think, but a similar flavor, that the formula A implies diamond A is also valid in every reflexive frame. Okay, so we just saw that the formula box A implies A is valid in all reflexive frames, but in fact, it actually happens that the exact converse of this is true as well. So not only is box A implies A valid in every reflexive frame, in fact it is only valid in reflexive frames. So in other words, if you find that the formula box A implies A is valid in a frame, then that frame must be reflexive, as a matter of fact. The way we're actually going to prove this is to kind of go the other way around by contraposition. You know that to show an implication A implies B is the same as showing not B implies not A. So we're going to do that, and we're going to show that if a frame happens to be not reflexive, then the formula box A implies A must not be valid in that frame. So let's take a frame W and R, which is and call it M, and suppose that frame is not reflexive. Then we're going to show that this formula box A implies A is not valid in that frame. So to show that something is not valid in the frame, well, it's supposed to be true for all formulas A, so we're allowed to find a formula A and a valuation and a world in the frame such that the implication becomes false at that world W, so which is to say that that W satisfies box A, but W does not satisfy A itself. Again, we are basically in the business of looking for a countermodel. The only difference is that this time we're not allowed to choose the frame. We've already been given an arbitrary frame which is not reflexive, but we are free to kind of choose a point in that frame. Now, the way to start here is kind of saying, well, the frame M is not reflexive, meaning that the relation R is not reflexive. Reflexive means that all worlds are accessible from themselves. So if the relation is not reflexive, it must mean that there is some world that is not accessible from itself. So there's a world W such that RWW does not hold. So we do not have RWW. Now, at this point, I'm going to take A to be a proposition. As I said, for most cases where you want to show that something is not valid and it involves some kind of formula variables, it's usually enough to just take those formula variables to be propositions. Now, here's something I'm going to do, which is probably the only really the only step that really requires anything which I would call invention. So I need to take a valuation for this proposition. I'm free to choose it, and I'm going to take it to be the set of all worlds in the frame except for this little w. Little w is the world that's not accessible from itself. Now, so P is true everywhere in the frame except at the world little w. Now, obviously, by construction, w is not in the valuation of proposition P. I've constructed it purposely that way, and the reason I did it is I wanted to make sure that P would not be true at this world W. So we have that the right-hand side of the implication is false, which is one of the things we need. The other thing we need is to make sure that the left-hand side of the implication is true. We need to make sure that box P is true at W. That's what we need to kind of show that the implication is false. But in fact, we must have that box P is true at W. Why? Because W satisfies box P if P is true at all worlds accessible from W. And we know that it must be because I made sure that it is true everywhere except W. And we don't have to worry about the fact that the P is not true at W, because we already know by non-reflexivity that W is not accessible from itself. So P is true at everywhere accessible from W for sure, because it holds all worlds except W, and so W itself satisfies box P. And then we're done. So we've managed to find some instance of this formula, box P implies P. And we've managed to find some world and some valuation such that the formula becomes false in that world, just assuming that the frame is non-reflexive. So the formula is not valid in that frame. The conclusion is that, that if a frame is not reflexive, then the formula box A implies A cannot be valid in that frame. So we've got now two results from the last two lemmas. One is to say that box A implies A is valid in every reflexive frame. And the other direction was to say that it is only valid in reflexive frames. So in fact, we have an equivalence from the last two lemmas, that box A implies A is valid in frame M. Remember, that's this notation here. If and only if the frame M is reflexive. So in other words, these two conditions, the validity of this guy, the validity of box A implies A, and the reflexivity of the frame M are exactly the same thing. So there's no difference between doing the following two things. On the one hand, I could say, I don't want to consider arbitrary frames. I only want to consider frames that are reflexive. That's one way that I could change the logic. And another way is I could say, I want box A implies A to be an axiom of my logic. I want this to be something which I've declared to be always true. But actually, there's no difference between doing those two things. You could even say, if you like, that the condition of being reflexive for frames is defined by the validity of this formula. Or indeed, you could say that the validity of this formula is defined or is exactly captured by the condition of reflexivity on frames. Yep, they are the same thing. And that brings us to the end of today's lecture. We have just one more lecture left in this series, and I assure you that fact is just as much of a relief to me as it probably is to you. So next time we're going to just finish off modal logic by spending a bit more time on the connection between conditions on frames and the validity of modal logic formulas. And then I'm going to give a few thoughts and tips on revision and how to prepare for the exam. So I shall look forward to that, and I hope you do too. Until next time, take care.